Okay, my wonderful students, let's get going. We're going to talk a little bit more about neutron stars today, and then we're going to talk about black holes. Now, this concept, Roman numeral 2, trapped photons, very short little phrase, that is actually the best way to think about black holes, and I'll try to walk you through it. Then, Roman numeral 3, we're going to of all the weird things that are true about a black hole, probably the I don't know, most unusual or uh, coolest is what happens to the dimension of time at the event horizon of a black hole. We're going to be doing a lot of clicking today, so get your clickers ready. And before we get to any of that, I mentioned last time the shock waves that are formed by a supernova detonation, and they cause certain exotic nuclear reactions to occur near the supernova or inside the shock wave. And that's how all the elements above iron on the periodic table are cooked up in those shock wave nuclear reactions. You can't get them in a regular star. You can't get above iron 56, but under certain conditions of a supernova shock wave, yes, you can. And that is similar to these images here of some naval aircraft. Just at the instant they break the sound barrier, that shock wave that we hear as a sonic boom um, causes a chemical reaction um, that we know as condensation to occur. So the water vapor in the air in front of the plane, right out here to the right here, it's just water vapor. But when that shock wave passes through, the shock wave is traveling with the plane. As it travels through that air, bam, for just a second, you get a flash of micro droplets under high pressure conditions, uh, and that's what you see as this. That's how you can see the shock wave that you can hear. You can hear it with your ears, no problem, miles away. But this, you have to be near sea level where the air is moist, a lot of humidity, and you have to be breaking the sound barrier. It's kind of cool. And here's another one, a similar plane coming close to um, head on. Anyway, so those are examples of shock waves. I wanted to show you last time and I didn't have those images. Okay, neutron stars, the leftovers from the supernova detonation. I want to show you some images from a pulsar in the constellation Vela. Now, Vela is not one that we can see easily from Florida. It's in the southern hemisphere. It's a southern constellation. But if we were down in Brazil or Argentina or something like that, Australia, you could see the constellation Vela. And, the Hubble Space Telescope can see it all the time. Now, this is an image of some shock waves and a jet. This kind of, it looks almost like a spiral here. And through the middle of the spiral is this jet of brighter blue stuff. And that is from this neutron star that we've been able to observe, among others, neutron stars in the sky. This one's in Vela. And the specs that I want you to jot down are simply, okay, 142. The specs that I want you to jot down are that its radius is actually that should be its diameter. Its diameter, so that should be capital D. I'll change it in the podcast. Capital D is 20 kilometers, radius 10. And then its mass is about 2.2 times the mass of the sun. So remember, a supernova will occur Not for our star, the sun. It's going to become a white dwarf eventually. Might become a red giant, but it won't become a supernova. You have to be heavier than our sun. And this one, after the supernova detonation, there's still a lot of mass left around. For this one, about 2.2 times the mass of the sun. Now, the reason I'm bringing that up is because, first of all, just the size, diameter of 20 kilometers is pretty small. And we're going to work with that in just a minute. But before we do that, I want to show you the density. If you compute the density of a sphere with this mass, this many kilograms, go ahead and write this number down. The density, lowercase Greek letter rho, 1.3 times 10 to the 17 kilograms per cubic meter. Now, this table up here, this lectern, it's maybe 2 cubic meters, close to 2 cubic meters. If this table were filled with neutron star matter of this density, it would be about 2 times 10 to the 6, 2.6 times 10 to the 17 kilograms. All right, now the mass of the sun is about 2 times 10 to the 30 kilograms. So even though you don't have a lot of mass here, you would still have, I mean, compared to the sun, it would still be a lot. Now, let's compare that to water. Water has a mass of about 1,000 times 10 to the 3 kilogram per cubic meter. So what that means is if I had a tank of water the size of my lectern, it would be about 2,000 kilograms of mass. Because this is about 2 cubic meters up here for this lectern. And each cubic meter in the lectern, if it were filled with water, would be about 1,000 kilograms. So a total of about 2,000 kilograms. Students, that's 2 metric tons. 1,000 kilograms is a metric ton. So this desk, this lectern up here, if we filled it with water, would be about 2 metric tons. That's normal. You know, you have water-carrying tank trucks. Gasoline is probably a little bit different density, but you have gas tank trucks, you know, carrying many thousands of gallons of fuel, many thousands of gallons of water here and there. And so that's the density if it's carrying water. Now the density of neutron star matter is about 100 trillion times that. Right now, that's the figure I want you to remember. The density of neutron star matter, it's all squished down underneath the supernova explosion so that protons and electrons get smushed down into neutrons, and there they stay till the cows come home, billions and billions of years. That matter is about 100 trillion times more than water that we drink here at the surface of Earth. Okay, that is very dense. So a spoonful of neutron star matter would be 100 trillion times more than a spoonful of water. So you take a tablespoon of water, it does just a few grams, easy. But a tablespoonful of neutron star matter, very serious indeed. Now, the size. The neutron star, about a diameter of 20 kilometers, my wonderful students, it would fit nicely into Orange County. Here's Orange County. All right, so up here in the upper left, okay, Mount Dora's out here. Popka's up here in the northwest corner. Upper right corner, Maytown. I've never been there. Scottsmore, been there. Geneva. Bithlow down here. Oh no, actually, this is outside of the county. Bithlow's up here, kind of on the east. UCF is right here. And down here, you're getting down towards Lake Nona. I think this is Lake Nona right here, this round one. Here's Lake Hart. And then down here, you're talking Disney, I guess down here, Lake Buena Vista, whatnot in the southwest corner. So that's Orange County. Okay, if you put the Vela pulsar, the Vela neutron star that we're talking about, and you touched it down right here at UCF, it would cover this much territory. All right, so it doesn't even get to downtown. Right, but yet it's 2.2 times the mass of the sun, so it's incredibly dense. Side note, in addition to what we talked about, is this: a white dwarf star, which the sun will eventually become, we think, is usually about the size of Earth itself. So a small mass star, final end state white dwarf, you're talking about the size of one of the terrestrial planets. And most of the time we compare it to Earth. Neutron star, the end state for many large stars, you know, maybe 10 times, 15 times the mass of the sun, about the size of, well, not even Orange County. Fits nicely inside the county itself. Okay, so here's UCF here, and these are actually the coordinates of Starbucks in the bookstore at the center. So if you touch it down there, here's the 417, Curry Ford down here, Bithlow over here, Chulioda up here in the northeast, Oviedo Mall out here, northwest. I don't know what this is, Aloma? Okay, that's the corner of Aloma and 436. So, you know, whatever. There's a, yeah, Semarin 436. So that's like there's advanced auto parts there, I know. Anyway, now final note about neutron stars. This one we can observe and measure, you know, get its size approximately, get its density, because it's part of a binary star system. And the other part is a blue supergiant. And so this one is big enough, this neutron star, that it will suck matter off the surface of that blue giant, and the blue giant will have a strong solar wind. And so a lot of that will end up swirling down and trying to get onto the surface of this neutron star. And that's actually the stuff that we observe. We don't really observe the neutron star itself. We observe the X-rays that it generates because it's sucking matter off the surface of its companion, blue supergiant. And it's about 1,000 light years away. So, yeah, that's a... And there's a lot more. You can read a lot about neutron stars. They're pretty mysterious. I've done some calculations on them myself. They are not easy. You have to know a lot of buku physics and calculus and stuff. Enough to choke a mule. Enough to choke a physics professor, as it has done for many. Only the proud can do that. The few, the proud, the maniacs. All right, let's check. Speaking of maniacs, let's talk about some black hole concepts. First question for you is just kind of a general concept, and everybody's going to get a point on this one. What is your favorite black hole concept? So, oops, let me, hold on a second. All right, here we go. Okay, question number 1, multiple choice. Frequency AA. Just take a minute and figure out which is your favorite black hole concept. So what, everybody's always fascinated about black holes. So let's take a look at your concepts. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys vote for. It's going to be a spread of concepts. Okay, 27% voted for a black hole sucks in everything around it. Very common concept. 15% of you voted for a black hole cannot be seen, so it cannot be measured. 19 of you voted for there's nothing inside a black hole. 46%, if you dive into a black hole, you come out in another part of the universe. That's interesting. That's the biggest one, 46%. And it's actually the case that none of these are true, so you're all wrong. But I'll give you all a point. These are all misconceptions. All right, and I'm going to correct your conceptions today. We're going to try to get some actual facts. I especially hate that other one. Oh, you dive in and you come out somewhere else in the universe. That's nice in TV shows and stuff, but it's here's the concept. This is the thing. This is the key. Outward moving light. This thing that you see here is a picture, a representation in perspective of something called a light cone. The light cone, C-O-N-E. And the outward moving light or inward moving light will always, and I'll show you how to do a light cone in just a second. Let's do some more clicking questions, and we'll build up the idea of a light cone. Question number 2 for today. The speed of light. How far does a photon go in 1 second? $20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys voted for. Uh-oh! We've got a few people that voted for B. The correct answer, that's it. 3 times 10 to the 8 meters. That's what that number means. If the speed is 3 times 10 to the 8 meters per second, that means in 1 second, that's how far it goes. All right, so make a note of that. This one here, B, that's, I think, the inverse of this number, but that's not right. All right, let's go to the next question. Oh, second side note is 3 times 10 to the 8 meters, that's 1 light second. Okay, that's how far light goes in 1 second. And we use light seconds to as a distance unit for instance, the solar system. The galaxy, we would use light years and hundreds of light years. But for the solar system, light seconds, light minutes is pretty good. All right, let's do another one. If you aim 2 photons, you might want to sketch this one out. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys voted for. Yeah, a lot of you got it right. 2 light seconds. And the way that you figure that out is just that this is, if it's a 60-degree triangle like this, and it's equilateral, then this side over here has to be the same size. So those two photons, make a note of this. See, we're trying to look at outward moving photons. And so if these two photons, if there's a flash bulb right here at the start, and photons go off in all directions, these two, after 2 seconds of travel, will be 2 light seconds apart. Now, if the other ones start out at a smaller angle, Matt, they'll be a different distance. If they start out going back to back, one going left, one going right, which is possible with a light bulb, flash bulb, then they'll have different distances. But these two, yeah. All right, now, here comes a brain burner. Graph paper, marked out in seconds vertically, light seconds horizontally, otherwise known as a space-time diagram. Talk to your neighbor, think it over. Think of where something would go at the speed of light. And this is one that you might want to make a sketch. At least sketch the graph paper. "30 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys got. Whoa. We got some splaining to do here. We got answers all over the board here. That's all right. Now let's take a look at this. If you travel in 1 second, if the distance you go is 1 light second, then that means that if you start right here, get my cursor over here. Come on. There we go. Okay, if you start right here, then in 1 second, you go up, and then distance-wise, you go over 1. Okay, so the rise over run, go ahead and make a note of that. For a photon, on this diagram, rise over run is exactly 1. That means that 45 degrees is the right answer. And the majority of you did choose that. The rest of you, make a note. That's why. Light always travels at the speed of light. So in 1 second of travel time, it moves 1 light second. So if it starts here, if this is where your flash bulb went off, where my cursor is, at 1, 1, then in 1 second, it gets out to 2, 2. Easy. All right. Now, go ahead and sketch in this one. This, fellas, you're talking on top of me. Don't do that. Sketch in this path of a photon. Now, this one's going to the left. Right? So make a note. This one's leftward. It's tilted into the northwest direction. So we would say it's going leftward. And this one's tilted to the northeast at exactly a tilt angle of 45. And so that one we would say is going to the right. Okay, so positive x values means to the right. And Time is always increasing. Everything that is inside this pair of lines, this shaded in blue area, everything in there is moving slower than the speed of light. So kind of shaded in with some cross hatching or some dots or something between these two 45-degree lines. That's everything else. Nothing can go faster than that. And everything goes slower than the speed of light. Everything other than light itself goes at a slower speed. So for something that's slower than the speed of light, in 2 seconds, you might only go 1 light second. All right, so that puts you right in about here. So that'll be a little bit steeper than 45. And something that's, go ahead and make a note of it and add this to your diagram, something that's stationary, at rest, vertical line, right along here. Okay. So everything in here is slower than the speed of light. And the term for this is a light cone. This is the side view of a light cone. If you think about X and Y axes on the floor and then time going vertically upward, then it would form kind of a cone shape that we saw earlier. Okay, so all matter will always be somewhere either on the very edge or somewhere inside the light cone. So if you have an atom of hydrogen here, sometime later you're going to find it somewhere in this greenish blue area. You're not going to find that atom over here. It's not possible. Okay? It's got to be inside the light cone. If it's a photon, if your photon is emitted here, it's either going to be right on the surface of the light cone or maybe on this surface over here. And in 3 dimensions, it'll be, it can have any, somewhere on the 3-dimensional cone. Okay. Now, what do photons normally do? Well, they cover distance. Okay. Normally, they travel in straight lines. And as we've mentioned, for every second of travel in space, it takes 1 second, or they cover 1 light second. All right. And the problem with that view is that it can change from straight line travel if there's curvature of space-time. Now, Einstein's theory of relativity for the structure of space-time, near a black hole, which is what we're talking about, even near a neutron star. Neutron stars will bend space-time pretty drastically. Not as much as a black hole, but they will. The sun bends the space-time. The sun, our sun, curves space-time. Earth curves space-time. Just a little bit. We can measure it, using lasers and stuff. And we can measure it using starlight with the sun. But yeah, curvature of space-time, the presence of a lot of mass, usually, or energy, will make space-time curve, and that will change what photons normally do. Now, another way of thinking about what photons do is, in 1 nanosecond, 10 to the minus 9th of a second, a photon travels 0.3 meters, 0.30 meters. That's 30 centimeters, about 12 inches. Go ahead and write that down. So if I have a burst of light, Drew, that lasts for 1 nanosecond, you're both listening to the same music? Excellent. Very good. So if you have a flash bulb that's lit for a nanosecond, then the first photon will be out here, and the last photon will be about here, about 12 inches apart, 30 centimeters apart. Okay, and they'll all be moving out in some direction. Okay, so that's what. So for instance, if you have a hydrogen lamp and you open a you open up the you have it in a box and you uncover it for a nanosecond, Eva, and then close it after a nanosecond. That'll be a nanosecond burst of H alpha, which we've seen before. And that'll produce a shock wave of photons about 12 inches thick. So, so go ahead and sketch a light emitting object, and let's go ahead and sketch in a 12-inch nanosecond pulse from the surface. All right, so my flash bulb here, if I turn it on for 1 nanosecond, a little bit later, all those photons are going to be somewhere out here in this red shell. So three-dimensionally, that would be a shell. It'd be a spherical shell of photons working its way out. All right, and it would travel every second. It would get another 1 light second away from the origin, and it would be spreading out. Underline that word, spreading out, because that is what photons do from a single source in ordinary uncurved space-time. Photons will spread out. All right. So this, you'll still have a 12-inch shell, but it'll be, covering a light second of distance, whatever direction it's going, for every 1 second of travel time. And after about 500 light seconds, if it was the surface of the sun, then those photons will reach Earth. But if you're near the event horizon of a black hole, no, no, no. Right? And so we're going to have some questions about black holes, a few more clicker questions. The guys that left early today, they shouldn't have left early. Let's do some more questions. Now this question here, I want you to think carefully about. Here's the law of universal gravitation. I believe this is chapter 4. And go ahead and answer that. 30 seconds to vote. Fifteen seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah. And here's how you can understand that. It's going to be stronger at the surface because the numerator over here, let's say that M1 is the mass of the Earth and M2 is the mass of the object that you're looking at. Yeah, it's M1 is in the numerator, so instead of the mass of the Earth, you have twice that. You're going to have twice the force of gravity. Right. Another question. All right, your manufactured Earth, twice as many kilograms, stronger gravity at its surface, good. How does that affect the escape velocity? In other words, how fast you have to get going with your rockets before you can say definitely that you're going to escape the gravity of this planet on the way to the moon or wherever you're heading. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, it's gonna take more because gravity's stronger. Okay, so make a note of that. And so let's talk about um, what we call an astrophysical black hole. In other words, a black hole that is left over after a supernova detonation. Okay. Um, Usually a black hole we predict is going to be 3 times the mass of the sun or more, depending on how big the original star was that went into supernova. Um, the neutron star is stable. It's going to remain a big blob of neutrons until the cows come home because it the the the, the density at which you pack neutrons has a fundamental limit that just because of the nature of being an electron you cannot exceed unless gravity is stronger, and that's the case of a black hole. So there's no more outward pressure force that will support the matter against collapse, so it just collapses down. And make a note of it, it collapses down to 0 volume. So when I said that, when some of you answered, what is your favorite concept? 0 volume. There's nothing in there. What it really means is that everything is in there that it started with. It's just crushed down to 0 volume, whatever that means. People still trying to figure out, what the physics. The problem is we can't get into a black hole and do some experiments and then phone home about it. Because once you're in there doing experiments, you can't send anything back to good old planet Earth. All right. Now, the astrophysical black hole. The common descriptions, which you'll find on page 366 in your text, and I believe that's chapter 14, not even light can escape from a black hole. So when I was asking you about escape velocity, yeah, that's one way to think about a black hole. It's an object for which the escape velocity is greater than the speed of light. And in page 366, they talk about that. Another thing that they mention on page 366, the event horizon, that's the surface or the point of no return. Once you start collapsing down, there's a point beyond which you're safe. If you're outside the event horizon, you're going to feel curvature of space-time. There's no doubt about that. But you won't be inevitably sucked down to the center of the black hole. There's a safe distance, which we'll go over in just a minute. And if you're outside that, no problem. If you have good enough rockets, you can escape back to planet Earth. If you have a laser, you can, do Morse code back to planet Earth. Okay? But once you're inside the event hole, forget about it. Photons, nothing. I don't care how strong your rockets are. You won't be able to make it. There's another way to describe a black hole, and that's what we're working on, the whole idea of a trapped surface. It is geometric, and a third way, and actually these things are misnumbered. This should be 4A and 4B, and 3A and 3B. I don't know what the software's doing that. Anyway, the ways to describe a black hole, the best way is geometric, in other words, using space-time concepts, 4 dimensions, as Einstein did. And then the other way is to think about entropy, which is the amount of information that you can send and receive. And both of these concepts are related to what photons do. So as I mentioned, the key is understanding what photons do. What are the photons doing? Especially the outward moving photons. Because outward moving photons of light are what allow us to learn what's happening in any point in the universe. In other words, if we're listening to astronauts on the moon, they've sent electromagnetic radiation from the moon to Earth. Okay? And we can think of that as photons. Okay? And so the amount of information that you send and receive, yeah, that's related to what photons do. Same thing with space-time. And what we're going to find, Drew, is that the behavior of photons is going to change drastically, especially near the event horizon, the point of no return. Question?
So in the case of a binary collision, like a binary star collision, black holes will also form due to a great amount of mass colliding, right?
Possibly.
Then how does a gamma ray burst sort of come from that? 'Cause
Yeah, gamma ray bursts. We don't really know what gamma ray bursts come from. That's Gamma ray bursts are high energy gamma rays that seem to come from random locations in the universe. We first observed them in the 60s when we had a satellite called, coincidentally, the Vela satellite that was set up to observe the Russians and monitor their nuclear testing by looking at high energy gamma rays. When it wasn't orbiting over at Russia, it was looking out into the universe, and we saw these strange gamma ray bursts. We don't know what they are, but we think maybe it's related to black holes. But yeah, two stars that crash together. I'm sure that's probably formed a black hole a time or two. It's interesting. That would be an astrophysical black hole and probably a spinning black hole. Angular momentum would change all the geometry of the spacetime. What we're doing is the geometry of a non-spinning black hole. But yeah, I mean, it's possible. All right, so let's go back to what photons are doing and what curved spacetime does to them. All right, if spacetime is flat, photons travel point A to point B along a fairly straight line, just like this. Here's a star, and here's Earth. And if you're not in a region of highly curved space-time, it'll just kind of mosey right on through. Just like here on the surface of Earth. We can model what photons do using straight lines. And when they go through a lens, the way that we do that is, a beam of light or a ray of light goes into the lens, and then it goes out at a slightly different angle, and hopefully it focuses where it's supposed to, and you can, use your eyeglasses and see. So that's normally what flat space-time does. It gives the photon just a nice straight set it and forget it, Elizabeth, all the way back to Earth. All right. Now, if there's a region of curvature along the photon's path, then we got some problems. And it's going to affect the curvature of the photon path. Now, this S here, kind of yellowish with a green layer, that represents the SUN. And our SUN has enough curvature. It's not very strong, but we can see it, its effect on starlight. So let's put this S up here. All right. Now, this star is behind the sun. And if there were no curvature of space-time, the photon that starts here at this star would just get absorbed by the sun, and we'd never see it. We wouldn't see it. It's behind the sun. Right? No problem with that. Right? But if there's some curvature, the photons, even though they don't have any mass, they'll curve. This one, here's a different photon, and it starts as if it's going away from Earth, but then when it gets close to the sun, it just grazes past the sun here, and it comes back down here, and we can see photons from this star along that trajectory. Photons will do that. Now, a photon, formally speaking, has no mass, zero mass. It shouldn't interact with the gravitational field at all. But it does respond to the curvature of space-time produced by the sun, and it does follow a curved path. Now, Einstein predicted that this would be the case. He said, we should be able to look at the sun and see stars behind it that we shouldn't be able to see. All right? And in the first total eclipse, after his prediction, which was 1919, they actually observed it. Now, here's what it looks like. This photon here is not going to get to Earth. Now, that's what we would expect if there was no space-time. We wouldn't see the star. But what happens is you see this photon that's gone on a curved path around the sun. It ain't, if there were no curvature of space-time, this photon right here that starts out at this other angle, it would blaze past the Earth. You'd never see it. But because it's just grazing past the surface of the SUN, you can see photons. Okay? And here's the angle that it comes in on. It comes in on this angle, and that is where the star appears to be. And for this reason, if you observe the sun or the stars around the sun during a total eclipse, it's got to be a total eclipse. So blot out all the glare of the sun, all right? You can see stars that you shouldn't. We shouldn't see this star. It actually is back over here. But because of the deflection of starlight, you can see it just barely peeking over the edge of the sun. And that, my wonderful students, is the very first verification of Einstein's theory. So underline the word there, verification. He predicted it. And by God, they found it. They measured it. They got it. And Einstein's theory is extremely well verified. It is solid like a ROCK. Right? The fancy term for this is gravitational lensing. Because this is what lenses do. A lens comes in, a ray comes into a lens, and then it changes path. Okay? And we model it as two straight lines, but in actuality, as the wave goes through the glass lens, it gradually changes direction. So, but we model it as a change of direction, just like this one. And Einstein said, if you go to the total eclipse in 1919 and look for a certain star or probably a couple, you should be able to see it if my calculations are right. And they looked and they found it right there. Right? Now that's what gravitation does. And here's another thing. I want you to think about this and make a note of it. Gravitational lensing. It's the opposite of photons diverging. Normally, photons will diverge. But in the presence of curvature, if it's intense enough, they won't diverge as much. This one diverged. It wanted to diverge, this dark dotted line. It wanted to diverge, but it couldn't because it interacted with the SUN. So it had just a little bit less divergence than we would expect. All right, now, let's talk about this. Go ahead and draw yourself a sphere or a circle of blue flash bulbs. And let's say that they all go off at once for 1 nanosecond. All right, so you've got a shell of photons going outwards. All right, and the photons are going to follow these paths. Here they are, and I've mapped out 3 of them. All right, here they are. Okay, and a little while after that, they'll be out here. All right. So my 12-inch shell of photons, if it's normal space-time, they just kind of cook out there and they keep diverging, no problems. All right. And so go ahead and make a note. Normal space-time, more divergence per second, larger area for the shell. Okay, so every light second or every second, the diameter of that thing gets bigger by 2 light seconds. So you get bigger and bigger spherical shell. So this is a side view, so it looks like a circle, but think about it as a sphere, and we're looking at a cutaway view of what a sphere is doing. And the area of that sphere will get bigger and bigger if they keep diverging. Underline the phrase larger area. because they're divergent. If there's no curvature, right? Now, let's take the same sphere of flash bulbs to the event horizon, right? Here we go. Flash, and they're aimed outward. And they try to follow these paths, just like the other ones. But because the space-time is highly curved, they will not diverge. Instead, they're lensed. They converge. They're converged so quickly and so thoroughly that they capture no more area. Okay, so make a note of that. No more area. They're blazing outward. They got their direction right, but it's just that the curvature is making them all converge instead of diverge. So they're not getting more and more surface area. They're stuck. They're trapped. And that is why we use the idea of trapped surface, a surface of trapped photons. The event horizon is the outermost location where you will find trapped photons. Okay, they're trapped. They started at the precise place where no matter how long you wait, they're not going to diverge and cover a bigger sphere. No more area. They're trapped. And that, my wonderful students, is the geometric way to define a black hole. The event horizon is the location of the trapped surface where photons are trapped. Now, here's something else that's weird. Light bulbs inside the event horizon, forget about it. Not only can't, the ones at the event horizon, they're kind of parked out there, they're trapped. Everything else, the curvature is even though they're aimed outward, their final destination is the center, inevitably. R equals 0. The very center of the black hole. We don't know how that, well, I shouldn't say we don't know how it works. We do know how it works. It works by relativity. But boy, it's a strange concept. And this brings us to the strange behavior of time at the event horizon. So if you're, reading page 368, they talk about, okay, what would happen to an astronaut that dives into a black hole? You're outside the event horizon, and you dive in, what happens? Well, you got a lot of troubles. Trouble's coming, trouble's on the way, and eventually you're going to, kind of like this picture. I mean, this is one of these M.C. Escher pictures where, yeah, this looks okay, but then when you compare it to this guy over here, whoa. And then forget about this guy up here. And look at this guy. There we go. So look at this guy over here. Forget about it. I don't know how that guy dreamed up all these images, but anyways, let's keep going. Spherical coordinates in and around a black hole. Now we're going to get down to the nitty-gritty of what happens to time, the fourth dimension, at the event horizon. The radius of the event horizon, it depends on the mass of the black hole. So if you have a 15 mass black hole, this would be, M would be 15 times whatever the mass of the sun. So it would be about 3 times 10 to the 31 kilograms. And then c squared, that's in the denominator, that's the square of the speed of light. And then capital G, that's Newton's gravitational constant. And then multiply that by 2, and that'll give you a number of kilometers. All right? And in astrophysics, we usually abbreviate that R equals 2m. So we don't have to keep writing all these dipsy constants here. Okay, so that's lazy bones astrophysicist lingo. The event horizon, or as we call it, the Schwarzschild radius. Schwarzschild is the guy that figured all this stuff out in like 1917. He was a soldier out on the Eastern Front for Germany, and he must have had a lot of time on his hands. Uh, Probably working the telephones or something. He's a smart guy, a physicist, about 31. And he figured all this stuff, and then he died, like the next year, not from wounds in battle, but he caught some kind of a illness, and then bam, he was gone. But he figured all this out, and we call this radius of the event horizon the Schwarzschild radius. Now, at 3M, that's a special position relative to the black hole as well. That's not an event horizon. It's what we call the photon orbit. In other words, a photon, if you aim it so it's going past, you're out here, the black hole's to your left, and you aim the photon forward, it will not go off. It'll go around in a circle. It'll follow a photon orbit at that precise location. And that's the only precise location for it. So if you just miss aiming it in the right direction, if you're just a degree off to the left, it'll spiral down into the black hole. If you're a degree off to the right, it'll eventually kind of motate out to planet Earth or wherever it's aimed. But right at that location, yeah, it'll take a perfectly circular orbit. Now, the other important point is r equals 0, the very center of the black hole. This is what we call a space-time singularity. And what it's really like is a hole punched out of a piece of three-dimensional graph paper. In other words, if you have a piece of graph paper and you have 2 points on it, you can lay your straight edge down and draw with your pencil between those 2 points. But if you have a hole punched out of it, you can't draw on the graph paper for 2 things on opposite sides of that hole that's been punched out. And that's what, you can go right up to the hole in the graph paper, but that's where you stop. It's the same thing with the singularity. You can't go from point A to point B via r equals 0. You can't do it. We don't know. The singularity, we're still trying to figure what happens there. And this is the place where people say, oh, you come in and you go out to another universe and stuff. Well, it's not actually true, but it sounds nice in movies. Now, the other extreme is r going to infinity. So in other words, far, far away from the center of the black hole, space-time flattens out. And we're out here on Earth in the solar system. The sun puts a little bit of a dimple to space-time, and Earth just a teeny, teeny little dip. But we're pretty flat out here. This part of the galaxy is pretty flat. Now, when you go to the center of the galaxy, we got that big galactic black hole in there. There's a lot of curvature down there, my friend. But for us, these are the 4 points. Schwarzschild, photon orbit, singularity, and then infinity, which is where space-time flattens out. Here's a picture, right? Here's, on the far left is r equals 0. Here, and this black half circle represents the black hole. 2m represents the event horizon. 3m is the photon orbit. And then here's an intermediate value, 12m. And then here's r going to infinity. And I put a squiggle here to symbolize the fact that, this is the r-axis going out. And what we're going to do now is try to map out what light cones do. All right? Now, if your question, 3m is the photon orbit. Okay, that's where a photon is perfectly happy to orbit until the cows come home at that distance. It's just the way that the equations work out. Now, let's say that you are in a spaceship. You're sent on a mission to to this black hole. So at Earth, way, way out here, at about 16 million times the mass of the black hole, you're outfitted with a blue laser, right? So mission control says, all right, give me that take your blue laser, and I want you to beam back in dots and dashes, Morse code, what's happening? And you say, okay, got it. Now, by the time you get here to 12 times the mass of the black hole, you're blazing out. It looks, and go ahead and make a note of this. To you, the laser looks blue. So if you shine it on your hand in your spacecraft, yep, still blue. But by the time it gets out here back to Earth, it's going to look green. It's being redshifted. Not because of your speed, there'll be a little bit of that, but it's being redshifted by the curvature of space-time. All right, let's bring it a little closer. How about right here? You're just outside the photon orbit, serious curvature action. You're starting to feel it. You check your laser. Okay, you shine it on your hand. Yep, still blue. And then you beam it back. Everything okay? I am out of pizza. Or whatever you're beaming back to Earth with your blue. But by the time it gets back to Earth, dude, that blue laser, they're going to get your message, but it's going to be redshifted all the way into red. And so the closer and closer that you get, you've got a wristwatch and a blue laser, your wristwatch is going to be cooking along. It's Timex. Timex always cooks along nicely. But if they are able to watch your Timex, they're not going to, it's going to disagree with their identical Timex up on the wall. Drew.
Can the blue laser be redshifted so much that it's shift out of the range of visible light?
Yeah, it will. So it can go down into infrared and so forth. And that's eventually what happens as you get closer and closer to the event horizon. It's called an infinite redshift. So let's take a look at that. Okay, time should run more slowly. This is a statement from page 368. That is incorrect. I hate it when I see people write that. It is not correct. What is correct is that observers disagree about time measurements. So this guy that's going into the black hole, his time, if you ask him, he's going to say, my Timex is functioning perfectly. He's got a heartbeat, right? So he times it, checks his heartbeat. Yeah, I still got 58 per minute. Everything's copacetic. But when he beams that information back, or if they, in their telescope, they look, say, that they have a really good telescope, a Hubble, looking at this guy as he goes in there, their Timex up on the wall is going to be completely off. They're going to be days, months, years ahead. Okay, they're going to go to infinity by the time he crosses the event horizon. So your clocks, if you're on Earth, your clocks are going to tick to infinity before you see the astronaut's clock tick, before the last one. But for him, he's going to say, yep, it's going to take me 37 seconds. So he can do a countdown, and after the 37th second, he's inside. For him, the passage of time feels normal, is normal, but he will disagree with a distant observer. And the difference is, he's in a region where curvature is strong, near the black hole, and there the distant observer back on Earth is where space-time is flat. So the clocks start to disagree. The laser beams start to disagree. You go from blue to green to red to infrared, radio, and on down. Okay? The outgoing photons get redshifted. So here's the bottom line for this observer. You'd see the wristwatch and the laser get redder, and then infrared, and then radio, and then, eventually, and your clocks would go to infinity. In other words, you'd be dead and gone before you saw him cross, even though if you ask him, it would take 37 seconds. So things are all messed up here. Photons are redshifting all over the place. Time measurements are in disagreement, but it all makes sense if you look at the light cones. All right, now here's what a light cone will look at, plus or minus 45 degrees. 45 degrees left, 45 degrees right. If you're out in flat space-time. If you're getting in close, all right, go ahead and put a little bit more tilt on your light cone over here. Make it a little bit tighter than 45. And then inside, so here we are. Now we're going to go inside the event horizon. And what happens? Two things. The light cone broadens out. So now it's below 45 and it tips over on its side. Here's what it looks like. Go ahead and sketch that. And so we're left with this. And I've sketched out the black hole now. What does this mean for the light cone now to be tipped over sideways and broader? What it means is that, all right, here's the time axis. The time goes right up the symmetry axis of your time cone. No matter what your time cone is, that's where your time axis is. All right, time axis is here. That's good. No problem there. But once you get inside the event horizon, there's your time axis. Whoa. And now your time axis is pointed directly at the singularity. And so what you say is the following. R equals 0 is in the future of everything. R equals 0 is now, it's inside the light cone of everything. And for that reason, you could call it the omnifuture, the singularity, R equals 0. Now let's look at a regular calendar. Every 60 seconds, you mark off 1 minute. Every 24 hours, you mark off 1 day. And you go from left to right, and then you cut around, you go back and do it again. Every day. And so a specific time, like next Tuesday, is inevitable. Write that word down and underline it. Inevitable. Now that's in flat space-time. Fourth comment. In flat space-time, we walk as much as we want, left and right, forward and back, up and down stairs, no problem. If we want to really go high, we use a rocket. We can do it. Spatially, we walk to and fro. But inside the event horizon, my friends, the inevitable event is a spatial location. It's not a day like Tuesday next week. It's a position, R equals 0. It is the destiny of everything because of that tipped over light cone. As a result, time becomes a walkable dimension. So the calendar has become a chessboard that you can move here and there wherever you please. The calendar of days has become a chessboard. And your future, so what is your future? Whatever your future is, make it a good one. That's all I can say. Now, regular homework in masteringastronomy.com and a mega review. I'll see you on Tuesday. You're dismissed.